Laura Branch, take it away.
Okay, thank you. So my name is Laura Branch, and I have been a teacher at Ernest Rigetti High School for 24 years. And this is actually me and a colleague of mine out in the Amazon rainforest. So I tend to like to go, just like all of the other geology professors, out in the field and learn science so I could bring it back into the classroom. So the title of my project is Absolute Age Dating Carbon Burial in the Monterey Formation using uranium-lead zircon geochronology. And so this presentation will go through all of that. And the picture up in the upper right-hand corner, that's a great picture of what the Monterey Formation would actually look like. And my mentor is Alil Antila. He is currently in Istanbul. So that's pretty cool. And then the faculty principal investigator is Francis McDonald. And yeah, so I got to meet him in the lab too. And so we talked a lot about what actually is going on with these zircons and also about the foraminifera that I started finding. Frank?
Yes.
It won't go.
It won't go. Okay, let's try something. There's something, maybe it wasn't selected. Now let's try now. There it is.
Okay, good.
Sorry.
So what is the Monterey Formation? Okay, and we are talking about Miocene. So that is about 17 million years ago. And what is it and why do we even care about it? And so according to Dr. Bell, it is a major source of oil in California. So any geologist would know that if you talk Monterey, you're going to think about oil. And so when I got the call that this is my project, and I was like, yeah, it's going to be oil. Not. But anyways, it's also an important link to the past climate change, and it's an important storehouse for carbon. The characteristics of it, and this is a stratigraphic column of it over on the right-hand side, is that it has very fine grains in it. So it's like a mudstone, just a mud that's turned into stone. It's silicious. It has organic matter rich. It's thinly bedded and laminated. So they're going to be coming off in little tiny beds. You can kind of see over in the stratigraphic column. And its age is approximately 6 to 17 million years. So when I thought about this, I also thought geologists always kind of places us spatially. And so you can see the map at the bottom where you can see part of a stratigraphic column with the different rock layers, but also really we're looking at Santa Barbara Channel area with some different collection sites. My collection site is not actually on the map yet because it's still an ongoing process, but it was, all my samples were collected from Arroyo Burro Beach. So. Again, when I thought about the Monterey Formation, this is another really good way of looking at it, is that it's about oil, right? And being a teacher from Rigetti High School, Orchid is on the map because of all the oil. And then I always have students say, where does oil come from? And they all say the dinosaurs, because I think there was a cartoon way off wind that were like, the dinosaurs die and then they become oil, and it's just not true. Okay, so they actually come from little plankton. And that is why we have tar on our beach. So I was kind of excited because I already had a bunch of oil stuff all ready for this project. And then I found out that it's totally not about the oil. So again, you can see all the little laminated beds in the Monterey Formation, but then we're not looking for the oil or even the tar on this. What we are looking at is it gives an absolute time. Okay, for the Miocene epoch or epoch. Okay, and what is absolute time? There's relative time as a geologist, or that students learn, where the oldest rocks are going to be found on the bottom and the youngest are going to be at the top. It does not matter what the age is. You just know that the stuff on the bottom is going to be the oldest and the stuff at the top is going to be the youngest. If you absolute date something, you know exactly what the age is in millions of years. These millions of years right here are part of this slide. They do not reflect what's going on in the Monterey Formation. I'm just using it to show that, yes, you can absolutely have a time, like you absolutely are, I'm 51 years old in a certain number of days. But in the Monterey Formation, there's little ash layers from different surrounding volcanoes that have these little zircons in it. And the zircons are the key to absolute age dating. So how do we use zircons for data analysis? Zircons only form in magma. And so inside the magma, you're going to have your little uranium pieces that keep growing around these little zircons. The elements, as you find them, and these are zircons how we were finding them, but they have a absolute or a known way of decaying, right? So their uranium decay into the daughter element of lead is a predictable rate, and the half-life of uranium to lead is actually 700 million years. So if we look at the uranium to lead ratios, you can find the absolute age within the Miocene Monterey Formation for these ash flows or ash falls. So to do this, and this was my big part of the project, is I had to use this technique called the simplified bentonite separation technique, where we take a sample. I did not actually go out and find the samples. By the time that I started this, they were already collected. But my mentor, Lil, he went out and he collected this sample, and he put it in a bag. The EA means that those are his initials for collection. The 23 means the year that he collected. The 1 is equal to the number, that was the first collection that he did in the year. The 12.0 on this means that is how many meters up he is in the entire Monterey Formation. And so what he had me do is he had me create 2 Petri dishes. There was one for the water separated dense minerals, and then there was ones for the zircons that I'm going to be picking. And then if he has to go back and look through and find something else because there was an anomaly, then I had to have another little container for all of the panned out waste that we're not going to use. But then he can go back. And I actually messed up in the lab once, and I had to go back and I had to go through the pan stuff that I already did to find a zircon. I accidentally dumped all the zircons down the sink. And now that's on video, so everybody's gonna go, no. Anyways, so what I did was I went ahead and I blended the sample in just a regular blenders in the grass blender. And I used that with about 1,000 milliliters of water, just regular old sink water. And then I put it into very large 5,000 milliliter beakers, and it just really speeds up that erosion process. And so really what you're doing is you're washing the clay out of the system. You're also washing the oil out. And there were a lot of these that had a lot of oil in it. And then I was really surprised when the oil kind of went down the sink. But I was like, well, I don't know about that part, but that's how the whole thing worked. After that, the panning is going to be used to separate the most dense particles. And I think that for my classroom that I would definitely get some pans because it was really, really fun to do. But this comes out of those beakers. So I wash out the beakers and I start panning these. So I'm just like a gold miner, except that I'm not mining gold. I'm actually mining little pieces of zircon. Most of these, that's what it looks like up that. All of the dark areas were the dense materials that were left behind. And then these will be the dense materials. And I finally put them into a little Petri dish. They're going to be zircons. They're going to maybe be, I believe Elil said topaz were these clear ones, but there's also going to be a lot of pyrite in there and biotite, which are just other dense minerals. Once I'm done with that, the hunt is on for microscopic little zircons. And so I would take the Petri dish and I would start looking through this microscope for hours on end. And I would take and I would look through all of these little pieces, and then I would find little zircons. So here they are. And here's a better picture of what these zircons would look like. And I would have to use some little tiny tweezers to pick out 100. And so that was their sample size, was 100 white specks of zircons. And while doing this, I started finding garnets, which was kind of cool. And then I started finding the foraminifera. And so there's my pictures of some that I actually was able to put aside and take pictures of. And that could be a whole nother project for students or even for other graduate students. Yeah, I know that you're the reigning queen of this, but looking at how was this all deposited at one time? And foraminifera are actually a benthic species, which means that they're the bottom dwellers. They live on the bottom of the ocean at the time of all of this deposition. So what does this mean? After we get all just the zircons, we have to go to the cloud lab. And I've not yet done that. I have a date on August 9th to go and do this the day before school starts. And what's going to happen is we're going to put our little zircon samples in through this giant cloud lab laser, and we're going to ablate them. We're going to just blow up everything. And the zircons are going to go into this machine, and they are going to, all the little pieces are going to measure the ratios of uranium to lead. Okay, and the ratios reflect the age of the grain. And again, these ratios are going to differ between grain to grain, sample to sample. I'm not entirely sure about this process just because I haven't gotten in there yet. This is what it looks like when it comes out of the computer. So you can see that this one is actually for this place in Hondo Beach. And again, this is sample data, so I don't have the actual data yet because we have not done it. But you can see that here's the sample, here's the concentrations of uranium, and then you have uranium, and then you have lead, and then all these different isotopes of lead, okay? And based on that, you can get the isotopic age. And why is this even important? Putting it together with the stratigraphic column, you can figure out this absolute age. And then I was like, well, what is a high school student even going to do with this information? What does the public do with this information? And what happens is you put this up. My part is only part of his main thesis. But if you put it up with other data that he's collected, such as total organic carbon, sedimentation rate that's going on in this area, the organic carbon mass accumulation rate, you can find out a lot of really interesting things. You can have the data that supports this idea that there is a warming and cooling trend during the middle of the Miocene, the middle of this epoch, okay? And what this is going to be the Miocene climatic optimum. And I put it in red so that it looks warm because that was the warming section of this. And then after that ended up going through, then you get the middle Miocene climate transition. And the reason why that's important is because during this transgressive sequence, which I'll go over in the next slide, but it is just a period where there's global warming, okay? There's relatively high carbon dioxide because the Antarctic ice sheet has retreated, the sea level has risen up, and now you have more limestones being deposited here. And then you get a cooling, okay? And this is all supported by my absolute age date part and all of these other parts that's part of his thesis. And what is a transgressive and a regressive sequence? Just in passing, it's when we have the transgressive one is where you can have the fining. If you look at the stratigraphic column, so this is kind of like the stratigraphic column, then you have the fining upward. So you have your coarse grained sands, and then you have some mudstones or some shales, and then you're going to have limestone. Once you have a regressive or a cooling sequence, then you're going to have the opposite that's going to go on, where you have the limestone at the bottom, and then a shale, and then a sandstone. And so scientists look at this, and then they can figure out what's going on with what the temperature is around the world. And so here are my conclusions. First of all, the data analysis of zircons tells researchers the absolute age. That was the point of the entire thing. We needed to age when this climatic event happened. Okay, the ratios of uranium and lead from zircons found within the Monterey Formation give that absolute age for that warming and the cooling within that area. And this data supports the theory of the transgressive and the regressive sequence of the Miocene climatic event. And for me, the personal connection was that I've always just taught relative and absolute time. And then I go, absolute time is something that's exact. There's zircons. It tells you exactly. Now I know the whole process. Now I can totally explain that to my students. And so I thought that that was kind of cool. Where am I going to go with this? I have three main ideas. The first thing is in NGSS, you always have a phenomenon. The phenomenon should be local. And so I always try, like I've been to the rainforest, but that's a big connection, but the kids can't go and see it, right? So the Monterey Formation as a phenomenon for the concept of dating, of absolute age dating in my geology class. The next one is to use this research to explore this Miocene climate warming and cooling within my chemistry of the Earth systems class, and writing some sort of curriculum that does that. And then the third one is to possibly get some sort of a mentor or a grad student or somebody, and then actually have my students pick zircons and use this simplified bentonite technique in my classroom, because I think the kids would actually like that. And then that might be a skill that they could use later on and be part of a citizen science project. The other fun extension would be for students creating an age dating profile about the life of a zircon in the modern age. What would it look like now? We just have some warming off the oceans in Florida. What would that look like now in the rock record? How would that be reflected? And how would we age date it? And finally, acknowledgements. I would like to acknowledge Alil. He is currently in Istanbul, but we actually communicated a lot via text and emails. So he is my mentor and PhD candidate. I believe that he's going to be done within a few months. And then Dr. Francis McDonald, he's the principal investigator on all of this. Adrian, he was a PhD candidate that kind of stepped in for Alil when he wasn't here. And Frank and Marilyn, thank you for all of your help and guidance. And Nicole and Bill for all of their ideas and their guidance during this RET program. So, are there any questions? Very different from yesterday, though, right?
So you haven't actually run your samples yet.
No.
But you are expecting them to be in the range of like 15 to
17. Mm-hmm.
So
yeah.
Just in terms of other things going forward, I have samples from the offshore. So I'm not looking at rocks, I'm looking at sediments. Not that old, but they would be things that samples that I could give you that your students could then sieve, which is how I just found through a sieve.
Well, that's really good because I actually have a class set of sieves.
Yeah.
So
if there's things that they wanted to look at,
that would be really, really cool.
Whatever else.
Okay. So next year, when I'm writing this all up, you're my contact person. So, any others?
So the zircons tell us the absolute age, and that is the push forward that you're trying to establish here in this project. You have to relate. So you showed us the labels, how Elio labels where he took the sample. That's something that is very important because that's how you can take the absolute ages that you are going to achieve and correspond it to that, like for example, the warming and the cooling trend.
Yes.
So will he do that just based on those the heights that he wrote down where he took them, or is there do you know anything else about that?
I don't know anything else about that. But what I thought about doing is having a bunch of stratigraphic columns that I've made of the Monterey Formation from my little area, and then putting the actual data that pops out from the data that I collected on those, and then have the kids kind of put together a piece of the puzzle. I don't know how that would look in the classroom, but I think that would be really good. And then if I don't use like I could get that actual data for your sieving project, that would be really interesting. So then the kids are actually doing something and then figuring out about absolute time, relative time, and a whole bunch of other information.
So basically, though, you can only get the zircons out of like the ash layers.
Yeah.
Right.
And there aren't that many ash.
That's why those points correspond to where they are on the sample data
Yeah.
you showed us. There's only a few
Yeah.
points because that's where the eruptions were, right?
So other than that, you have to run,
Yeah.
you know, like oxidizers.
Yeah. Oh, where is that slide?
Wouldn't ash be sometimes spread both on?
Yeah, so that's why they're using them, because they can connect it. You can get a date on this, and then you can connect it to some other ash
there
at some
it is.
other site. But other than, you know, you still have to run the date, but you don't know exactly. Okay, we think this ash is the same as that ash, but we don't know for sure.
And some of the ash came from like volcanoes from like Moro rock or the ancestral Sierras or somewhere close. And some of them have come from like the Sierra Nevadas. And so I'm not quite sure about that process. It's probably looking at half-lives again. And I know that some of the zircons that I pulled were very eroded, like rounded. And some of them were very pristine, like they literally came out of the volcano and just deposited right there. And so they're in the rock record very, very pristine. And the other ones are kind of eroded down because they've transferred through the river system. That part I got from Adrian. So that lunch was very helpful when I talked to him. So.
Did you get a sense when Eliel took these samples? Did you get a sense that he was going right for those intervals that he thought there would be pyrites?
Not pyrites, zircons.
I apologize.
He was going for the ash layers.
That's right. So he
knew exactly where the ash layers were.
Got it. Makes sense. Yeah. Okay.
So, and he gets along little rocks that like he's like, just a minute, and then he goes, and he's like, I'm not supposed to take this, but just a minute, and then he comes back with little bags.
All for science.
All for science.
The pursuit of science is a noble.
Well, it was,
you were his spotter. You were his spotter.
I was a spotter. So.
So it's not something we can get our kids to do.
No, you can do it, just not where we were the day that I saw him up in Pismo Beach. He didn't. Like he's like, do you know something? But you know what? I'm not going to say anything else.
Yeah.
But if you went to the cliffs out here and you went to the Monterey Formation, and then that's fine. But sometimes the city council doesn't like people just helping to erode. You know what I mean?
Yeah.
But if you went to Arroyo Burrow and then you went on a trip out there, I'm actually in talks with my the Dr. Schroeder at Allen Hancock College, trying to get a field trip between her class and my class, collecting some of this stuff. And so I don't know what it would look like yet, but.
Wonderful. Thank you. If there's no other questions, we should keep moving, and thank you.